In this video, we're going to be taking an in-depth look at Pandas TA, which is one of the biggest and most popular technical analysis libraries out there. And what makes it even more amazing is how integrated it is with Pandas, so that we can easily append new series onto our data frames with our technical indicators. I'll be covering how to source data using the built-in yfinance integration, as well as 3 different ways of interfacing with the library in order to get the most out of it. I'll also be covering some small miscellaneous details like how you can use multiprocessing in order to speed up the calculation time, which is important if you're calculating a lot of different results. So we'll head on over to this Jupyter notebook I've got here. Of course, you're going to need Pandas and Pandas TA installed if we wish to do anything, so it's worth importing those. As far as fetching data goes, as I mentioned just then, Pandas TA has a yfinance integration with it. And so if you have yfinance installed, you can create a blank data frame here. So this is just an empty data frame. And then if you call df.ta.ticker, and then include the name of the stock or the asset, however it appears on Yahoo Finance. So if we go to Amazon here, you can see this is AMZN. Whatever is in those brackets, that's the symbol that you'll want to use if you want to request the data using this method. And so when we print that out, we get something that looks like this here. So if I run these 2 modules here, we get open high, low close, volume, and we also get some data about dividends or stock splits. By default, it's going to fetch daily data for us. You can change that if you want to. So instead of just providing the name of the stock, you can provide an interval and a period. So the period is going to be the amount of data that you want it to fetch. So do you want it to fetch a month's worth, a year's worth, etc., etc.? And the interval is going to be the time frame of the bars. So do you want minute bars, hourly bars, etc., etc.? yfinance does have limits on how much data that you can request. So for example, if I try to request, say, a year of hourly data here, let's see what happens if I print that out. Let's try requesting 5 years, crank it up a little bit. You can see we now get this error here. It says you can only request 730 days of 1 hour candles. And if you use minutely data, I believe it's only 7 days. So do be wary of that. Of course, you're free to use your own data source. As long as it's in this format where you have a date time index, open, high, low, close, volume, you'll be good to go really. So I'll put this down to 1 month again, just so we can have our data frame here. Looks like when this errored out before, it assigned none to df here, so we'll have to go back and grab our data. These df.ta functions are only going to work if df is actually defined as a data frame, so do bear that in mind. So print out our data again, and we can see that looks fine. So that's all well and good, but how do we actually run indicators here? Well, all of the documentation for Pandas TA is contained within the code itself. There's no hosted docs, at least at the time I'm recording this video. So if you want help on anything, just use the built-in help command on a Pandas TA object that looks like it might be vaguely related. So you can see here, if you do help df.ta, that's going to give you this long doc string here, which you're more than welcome to peruse. But if you just want the list of indicators, well, you can grab df.ta.indicators. Again here, make sure df is actually a data frame that's been defined. It can be empty, but otherwise this accessor here won't work. I'll go into more details about why it's df.ta a bit later on. But as you can see here, we've got a massive amount of different technical indicators that we can call here. So all of these different ones, these are just the technical indicators. And then we've also got a bunch of candlestick patterns. most of which are inherited from TAlib, which is a different library that implements a lot of these different candle patterns. And obviously, just knowing the name of the indicator doesn't necessarily tell you much about it. So once you grab the name from here, so say the aberration, you can come down here and you can run help on that, so ta.aberration, and that'll tell you some more details about exactly how it's calculated, what kind of inputs you can put in and that kind of thing. So we can see here from the signature of the function up here that it takes in the high, the low, the close, and then a few optional parameters here like the length, the ATR length, and the offset. If I were to go grab another function here, so let's grab the CCI here, I can do help ta.cci. It'll usually give a link to a page explaining how that particular indicator works, and you can see all of the different inputs that you can use. Like I said before, Pandas TA is a little bit unique among most modern Python libraries in that it doesn't really have hosted documentation. It's all contained within the code itself, and so you have to use this help function in order to guide you along your way. You can, of course, just search through the repo itself. So if you go to the GitHub page and you search for CCI, for example, you'll find a Python file dedicated to calculating that indicator, and then you can read through it yourself. But most of the time, it's way easier just to call the help function here, and that'll tell us what's going on. So we understand how to find each of the indicators and how to find information about a specific one. Now let's go and actually calculate something. So broadly within Pandas TA, there are 3 ways of doing things at 3 different layers of abstraction. The first one here, the most simple and basic, and to be honest, the one that I use the most often, is just directly calling a function. So I pick an indicator that I want, in this case the RSI, I run the help function on it to see what all my different parameters are, and then when I want to calculate the indicator and just add it to my data frame, I just run ta dot whatever the indicator is called, so ta.rsi in this case, and then I just manually pass in all of the different parameters. So the RSI here just takes in the close, and there are these optional parameters that you can put in here, like the length or the offset here. So I've just passed in the close and the length, saved that to a new variable, and when I print that out, that looks like a pandas series here. It's worth noting that you don't actually have to provide the close in here. So if you wanted to get the RSI of the open or the high or any other time series, even the volume if you wanted to, you can just pass that in here. It doesn't have to be the close, it's just the variable is called close. I'll run this just to make sure it's working here. There you go, you can see our series is being produced. And like I mentioned, I could change this to volume if I wanted to here, and that would calculate the RSI based on that. Having a series on its own oftentimes isn't that useful. We'd like to be able to stick that series back onto our data frame. And the simple and straightforward way of doing that is to just run the function as we did before, so ta.rsi and then all our different keywords. And instead of just assigning that to a random variable, so instead of assigning that to RSI, I'm instead going to assign that to the RSI column of this data frame. And that way, when we print out the data frame, we now have every column that we had before, but we also have this extra RSI column. So if I run that, it looks pretty much the same as it did before, but we've got our RSIs added on here for whatever kind of signaling that we want to calculate next. So that's the simplest way of using Pandas TA, and if you're comfortable with that, you don't really need to go any further with the library. You can just repeat this process of looking through all of the different indicators that are defined by using the help function, zooming down to documentation for that particular indicator by using ta dot the name of it, so whatever the name is in that printout, you can use the help function on there, that'll give you more information, and then you can just directly call that function like you would any other Python function with the parameters that it tells you that it needs. You can get very far in Pandas TA just using that. You don't really need much else. But the next two features I'm about to show you can be massive for quality of life. So the next way, and the slightly more abstracted way of using Pandas TA, is to use this data frame accessor here. So you've got a data frame, and then you call df.ta dot something. So this .ta here, this is new in Pandas TA. This doesn't come directly with Pandas. There's a whole section about how you can add external modules and extensions to Pandas on the Pandas documentation here. And that's what the author of Pandas TA has done. And so what this does is it shortens our notation, so we don't need to write quite as much. It's a lot less writing than what we did before, than something like this. And it also allows the function to automatically infer which columns it should take in. So if we take a look at the help for the Bollinger Bands here, so help ta.bbands, if I run that, you can see that needs the close passed into it, but we didn't pass the close in over here and it worked just fine. The reason for that is because you're saying on this particular data frame, I want to access Pandas TA and then run the Bollinger Bands on this particular data frame. And Pandas TA is smart enough to infer from the column names which ones are the open, high, low, and close. And so without us having to explicitly mention it, it can grab the closing price for us, which is quite a nice feature for us. As you'll notice that the Bollinger Bands here take in close without a capital letter, and yet it's able to infer that this close here with a capital letter is that same close. I'll show you how that works in a little bit. So we can scroll back down here, and that's the basic method here. So df.ta.bbands. And what that's going to do is just print out a data frame with all of this relevant information about how the B-bands are working. And then if you want to append this entire data frame onto our existing data frame, all you have to do is provide append equals true here. So if I print out data frame up here, you can see it's the same as before. We've got a regular open, high, low, close plus the RSI. If I now run this over here, so df.ta.bbands, but with append equal to true, it will now add all of these columns onto my data frame here. So if I run this, and then we run our data frame here, you can see all of those columns have been added on here, which is definitely way more convenient, especially when you've got multiple columns that you need to append. So I mentioned before that Pandas TA was able to infer some of the column names. This dictionary here is basically how it does it. So you can see if I provide the open column with a capital O, it will actually translate that to an open with a lowercase o. Same with all of these different names here. You'll find this in core.py if you want to go hunting for it. It's just a nice quality of life thing so you don't have to continuously change the headers of your Pandas data frame, as some data providers will use capital letters, whereas some won't. Another thing that we can do that I haven't talked about here is we can chain our indicators together. So what's happening here is we're calculating the sum of the open, high, low, close candles here, or rather the average. So we're adding them all up and dividing by 4. That's what's happening here. But then I'm passing that into a EMA function here. And in that way, I can chain everything together. So I can get the average of the 4 values. I can apply the EMA to that. And then if I wanted to append that to our data frame, super simple. I just have to pass in here append is equal to true. So I'm hoping you're starting to see the power of this slightly more advanced, more abstract syntax here. Another thing that you can do just to make life a bit easier is you can set a prefix and a suffix here. So you can see this says test EMA10, OHLC4. So I've applied a suffix of OHLC4, and we've added a prefix of test. This is very helpful when you're distinguishing it from other indicators in the data frame, as you might have multiple EMAs and you want to add something on there to explain which one is which so you don't get confused later on. The third method that we're going to be using here is called a strategy. And what this is very useful for is if you've got a bundle of different indicators that you typically want to calculate together on a specific data source, rather than having to type them out every single time or write a function to do it for you, you can instead create a strategy object and then run that strategy on a specific data frame. So I'll grab a fresh set of data here just so we get rid of all of the rows that we appended on earlier. And I've got this strategy here, which I ripped from the documentation. You have to give it a name of some kind. And then inside this TA attribute here, you provide a list of dictionaries. And each dictionary object is going to be one new indicator that you're calculating, which can translate into multiple columns in your data frame. So for example, if you're calculating the Bollinger Bands, I think you'll end up with 5 extra columns to account for all the different bands and the differences between them. So we can see this strategy is calculating the average of the open, high, low, close. It's taking the SMA of length 10, so you can pass parameters in here as well. It's calculating this indicator. And then this one at the end here is using chaining. So it's calculating the EMA here of the OHLC4. So that's what we calculated before up here. And you'll notice that the column name of this indicator, once it's calculated, is OHLC4 in all caps. So what this is doing here by referencing that column name is saying, okay, calculate this indicator here, and then pass whatever you calculate into this as the close parameter. And then, of course, we add a suffix to this EMA so that you can distinguish that this was calculated from the OHLC4 as opposed to just on the close value like you would traditionally with an EMA. I suppose there's no reason why you couldn't use a different column here, so perhaps I could grab the SMA that I'm calculating here. So instead of running this value through it, I'll run the SMA underscore 10 because that's the column name which will get produced here by this SMA. Let's see how this works. It seemed to run at least, which is nice. That means it probably calculated everything correctly, even though I passed in a completely different column name there. So that's the basics of running a strategy. One thing that you can do if you're feeling adventurous is you can run literally all of the indicators in the module on a given data frame by doing df.ta.strategy as normal, so running a strategy, but pass all in as a string, and it will run every single indicator that it has installed, every single candle pattern, with their default values on that data frame. So if I run this here, I think it'll take roughly 3 or 4 seconds to finish. It'll give us a few different warnings here, but you can ignore those. And you'll see we have, I think, like 200 different columns here. It will calculate all of these default values, which I don't think is majorly useful, but it's cool at least. You can see in all the columns here just how many different indicators were calculated there in a relatively short amount of time. It's probably a good time to mention that if you use a strategy like this, the indicators are calculated using multi-processing. So it'll use more of the cores on your CPU and therefore calculate much faster than if you were to just limit it to a single core. That's one of the main advantages of using a strategy object like this, is that it can be easily parallelized, which if you've got years and years of data, say 1 minute data, that can make a real difference when it comes to your execution time here. If you want to see what the difference is with and without multiprocessing, you can just change the amount of cores that are used here. So you can do df.ta.cores is equal to 0, and that will set that equal to 0. So you can see the last run over here that we did, I think that took 5 seconds. It may have been hidden somewhere now, but I believe it did show us earlier. Whereas this one seems to be taking more like 10, 20 seconds here. Something worth bearing in mind regardless. Now, one thing that I find frustrating about these strategy objects here is that when the columns are made here, the default naming convention is to give the name and then underscore and then the first parameter and the second parameter, so on and so forth. But oftentimes we'll be passing different parameters in here. So for example, by default, this length is 10 here. So if we were to run this strategy by default, if I were to get rid of this length here, this column would be named SMA10. So if I run that, you can see this column's called SMA10. But if I were to pass in a different length here, so length is equal to 20, for example, it would now be called SMA20. Now, while this is quite clear, this can be an issue if you're relying on that column being there later on in your program. And so one thing that you can do to combat that here is you can provide the names of the columns that you want that to be saved as. So let's say instead of having this variable column name here, I just want it to say SMA. No matter what length I use, I just want it to say SMA. To do that, I can provide a tuple here. So the key is call names, and the value is a tuple of strings. So it depends on how many items you're returning here. In our case, the SMA only returns one column. So all you do is you have a tuple with one element and the name that you want in there. I just want it to be called SMA. A tuple with one element, you have to add a comma on the end there. Otherwise, it won't recognize it as a tuple. If you have multiple elements, you don't need to do that. So you can see here for this indicator, it returns 3 different columns, and you just provide the names of them in this tuple. And then when we recalculate it here, you'll be able to see this column's now called SMA, which makes it much easier to reference later on in your program. And for me, at least, I find reduces problems later on. You could, of course, give the converse argument that the column name with the parameters is much more clear, as then when you extract all of the SMA columns, you can see which one's which. There are arguments on both sides here, but I just thought I'd show you how to rename all of the columns. Unfortunately, renaming the columns here does have a cost associated with it, in that multiprocessing doesn't now work. The indicators are just executed from top to bottom. As soon as you start messing with the column names here, that stops the multiprocessing from working here. So I think if I do call names here, you can see all strategies use multiprocessing except when using call names. Just something to bear in mind, and again, a bit of a trade-off there. It's all dependent on your needs. Finally here, one thing that we can do is instead of running all of the indicators, we can just run a category of indicators. So for example here, I'm running all of the momentum indicators that exist. So that'll likely give me the RSI, the awesome oscillator, stochastic, various other ones. Or for example, you could run all of the candle strategies. So I think if I change this to candles, this will run all of the candlestick indicators. You do have to have TAlib installed, I believe, for this to function properly. But you can see here it's spitting out different results for all of these different candlesticks. I think there's like 70 of them. And if you want to find all of the names of the different categories, they're all here. So there's momentum, candles, trend, volatility, etc., etc. That can be quite useful if you want to, say, calculate all of the momentum indicators, figure out whether they're bullish or bearish, and use that as an aggregate rather than just relying on one particular indicator. Or perhaps you could take all of the candles, figure out whether they're bullish or bearish, compare that with the momentum, and look for divergences. Many possibilities await us with the power of this library. And so I hope that you've learned enough of Pandas TA here to go out and explore and build your own strategies and be comfortable at all three layers of abstraction, from just calling the functions to using the data frame accessor through to writing strategies, leveraging multiprocessing, all that good stuff. And so I hope you enjoyed the video, and I'll see you in the next one.